Thanks for coming today. My name is Peter Duveen. I'm your host, and today we're going to explore some questions about uniformly accelerated motion. Uniformly accelerated motion in a straight line beginning from rest can be represented by this interesting graph here. I can draw it fairly well. I'm going to put this as a time axis, and this is going to be a velocity axis. And I will draw an approximately straight line, and that will represent the uniformly accelerated velocity there. Let me just bring this down here, and I'll make this a time t, and right over here is the velocity v. And this line, which describes a uniformly accelerated motion, can be written by the equation v is equal to at, where a is a constant that doesn't change when the velocity and the time change. So a is basically the slope of this line, and we call it the acceleration. So it's also referred to as the rate of change of the velocity. Now, so we can see in this motion that the velocity starts at 0 and it uniformly increases up through the time t to this velocity v. Now, what we want to do is to try and establish an equation that will give us the distance traveled when velocity is varying in this manner. We already have an equation for the distance when the velocity is constant throughout the interval t. It's simply E equals vt. That's simple. That's for uniform velocity. That will give us the distance. However, in this case, we have a constantly changing velocity. So the question is, what will be the distance generated over time t when the velocity increases uniformly at a rate a? And that is what we are going to try to coax out of this graph, and by being a bit clever with our arithmetic or algebra, however you want to call it, or analysis. And this is how we propose to do it. We're going to divide this interval t into a lot of small intervals equal in size. And in fact, we're going to divide it into 2n minus 1 intervals. And so therefore, each of these intervals, draw up here and see them. Take it a little bigger than 1, 2, 3. Maybe have an nth interval, some in-between interval here. Okay. And then finally, make 2 intervals at the end. There's 2 intervals at the end, and this just represents a middle interval. Now, I'm going to divide t into 2n plus 1 interval, 2n minus 1 interval. So, and I'll show you why I picked 2n minus 1 in a minute. This is a carefully constructed argument, which is needed in order to make life easier for us. So each interval is going to be equal to t over 2n, 2n minus 1. Now, all this means is that if I decide to break this up into 3, let's say n is equal to 1, then 1 times 2 minus 1, that's 1 interval, that won't work. Well, let's try 2 times 2 is 4 minus 1 is 3. So that would, if n is 2, then we've broken this up into 3 intervals. One the center 2 on each side. So, and could be any integer up to 20 million. But nicely, what we've done is we've very carefully been able to break each interval up into 2n plus 1, and we're going to change the number n for our convenience later on. That's why we're leaving it as n. So, secondly, what we're going to do is, in each of these intervals, we're going to try to get an estimate of the distance traveled. Now, there are two ways of doing that. Let's take our second interval, okay? This is our second interval. I want to show you something. We'll call this V1 for the moment. Our second interval, the velocity starts at V1, and it goes up to V2. Now, if the motion continued at V1 throughout the second interval, then we could easily estimate the distance, but it doesn't. It increases to V2. Likewise, if we used V2 to calculate the distance, we'd be overestimating the distance that way. So we could either underestimate or overestimate the distance traveled in that triangle by either choosing V1 or V2. What I'd like to do for all these intervals is to first overestimate and then underestimate. And we'll see how the distance actually traveled will fall in between the two. I'm going to overestimate the distance traveled in each of these intervals, each of these 2n minus 1 intervals, by using the maximum velocity as the kind of uniform velocity traveled in that interval instead of the actual change in velocity. So I'll be overestimating the distances in each interval, and then I'm going to sum them all up, and I'm going to get a total overestimate of the distance. But we'll see that as we choose more subdivisions, our result will approach a particular number. So let me start here. I'm going to be using this formula to get the velocity at each point here. And as I said, I'm going to use the maximum velocity in the interval. So in this first interval, we're going to be, at the end of this first interval, the time is going to be t over 2n plus 1. That's exactly that much time. And then I'm going to multiply that by the acceleration, and that will give me the velocity, the maximum velocity during that interval. Then I'm going to multiply it by the time interval again, which will give me an overestimate of the distance traveled during that interval, t over 2n plus 1. And I'm going to add all of these up, and my total, I'm going to make a total distance. Note the distance is going to be less than this, less than or equal to all of these added up as we go on, and it's going to depend on the number n, what we use for n, how much greater than the actual distance it is. So I'm going to then do the same thing for the second interval. I'm going to say plus, going to be the acceleration times the time, which is 2 times our unit interval here. So it's going to be times 2 times t over, what did I say, 2 plus 1? I suppose 2 minus 1. Very important, 2 minus 1, not 2 plus 1. T over 2n minus 1, I mean. And then I'm going to multiply it again by t over 2n minus 1. Okay. Because the second 2n minus 1 is just the amount of time interval multiplied by the velocity should give us our highball estimate of the distance traveled during that interval. I can then, I could go on. The next one is going to be 3, so I could go on. I'm not going to do the third. I'm going to try and cut the time down a little bit. I'm going to go all the way to the last 2 now. This is going to represent the nth interval, by the way. I'm going to go to the last two, and this is going to be n minus 2, and this is going to be n minus 1. So the nth minus 2 interval is going to be plus a times n minus 2 times t over n minus 1, 2n minus 1. Oops, I'm making another mistake. It's not n minus 2. It's 2n minus 2, one less than the last one, which is 2n minus 1. It's 2n minus 1. Sorry about that. Times the interval itself here, which is going to be t over 2n minus 1. And then I'm going to end with my final number, which is going to be acceleration times the time, which is going to be 2n minus 1 times the time over 2n minus 1 times the time interval itself, which will give me the overestimate of the distance, 2n minus 1. Okay, so now we can factor out each of these has the term a, t, t, 2n minus 1, 2n minus 1. So I want to factor that out. So again, d is less than or equal to a times t squared divided by 2n minus 1 squared. Then all we have left in the brackets are 1 plus 2 plus 3 plus n plus 2n minus 2 plus 2n minus 1. Well, what do you know about that? So what I'd like to do is add all these up, and now you'll see why I chose this number 2n minus 1. I want to pair the numbers off, the number just before n and the number just after n. The number before n is n minus 1. I'm going to add it to the number right after n, which is going to be plus n plus 1. And what the ones cancel out, the minus 1 and the 1 cancel out, we're just left with 2n. And I can pair all of them like that. So I'm going to have n minus 1 pairings between all the numbers after n and all the numbers before n, including, we could look at the last one. We're going to have 1 plus 2n minus 1, which also gives us 2n. So we're going to end up with 2n, the addition of 2n, that's our final result for each pair, and they're n minus 1 pairs. So I'm going to say n minus 1 times 2n, and then I'm going to multiply it by my other stuff, a t squared over 2n minus 1 squared. And one more thing I forgot, even though I paired all of the numbers on either side of n, but we forgot to add n itself, so we better just add n. Okay? Now, let's look at this then. This expression is a number for all of this. And it's going to end up, I'm going to expand this and expand this down here. So this is less than or equal to t. I have t, which is that distance. It's going to be less than or equal to a t squared over 4n squared minus 4n plus 1. Hope I did that right. times 4n squared. Nope, not 4n squared. No, it's 2n times n. 2n squared minus 2n plus n. Well, 2n plus n is going to give me minus n. How about that? Minus n. Very good. Okay. Now what I'd like to do is divide the bottom and the top by 4n squared, and that's going to end up giving me b is less than or equal to a t squared divided by 4n squared divided by 4n squared is 1 minus 4n minus divided by 4n squared is just 1 over n plus 1 over 4n squared and let me do this right. This has to extend all the way over there. Not very straight, I'm afraid. But that will give us the denominator here. This n looks like an h, but it's n. Okay, and then times 2n squared divided by 4n squared is just 1/2 minus n divided by 4n squared is going to be 1 over 4n. Okay. Now, if we look at this, we're going to be able to, I'm just going to put this over 1 so make sure we know what's going on. Now, we could put many values in for n and we'd get something interesting, but if n keeps on increasing, we'll notice that these terms go to 0 and this goes to 0. Therefore, this term here approaches 1 and this approaches 1/2. So we're left with basically what amounts to 1/2 a t squared, which will be, which means that the distance cannot exceed 1/2 a t squared, because 1/2 a t squared, remember our upper level estimate, our distance had to be less than or equal to that. So the distance must be less than or equal to 1/2 a t squared. Now, if we took all the low-ball estimates and started with a low-ball estimate for this one here, we would have 0 for this term. And for this term, we would low-ball it at this velocity. That would be a times t over 2n minus 1. And that's just what we have here, times 2n minus 1. So our low ball estimate for the second piece is just the high ball estimate for the first piece, and that keeps on going. So we have a low ball estimates for all of these going up to our last one is the same as our high ball estimates for all these up to this one. But our high ball estimate includes our last piece, and being a high ball estimate, it's the last term. So what we need to do is subtract this term and we'll get our low ball estimate. And this term ends up being just 2n plus 1, 2n minus 1. So as we go down here, all it would mean is that we would subtract from this term here 2n minus 1. Remember, this turned out to be 2n squared minus n, and we can say then the low ball is going to be 2n squared minus, notice it now, minus 2n plus n minus n, and we want to subtract from that minus 2n minus 1, so then it ends up being 2n plus 1. So we end up getting 2n squared minus 3n plus 1 for our low ball estimate. And let's see, is that actually less than that other one? Yeah, it's a little bit less. You see, you have 2n minus n, we're subtracting minus 3n and 1, yes. So it's a little bit less all the time. And, but if we divide this by our 4n squared, if we divide this by our 4n squared like we did the other one, we're going to end up 4n squared, 4n squared, 4n squared. We end up getting 1/2 minus 3 over 4 times 1 over n plus 1 over 4n squared. And what does this approach? This also approaches 1/2. So we know that d, meaning this approaches one, this even in our low ball estimate still approaches 1/2. We would replace this by, this here, and we end up getting the same limit, which is this is what remains as n approaches infinity, and this goes to 1, so we end up getting 1/2 at squared. So finally we have 1/2 at squared is less than or equal to d, is less than or equal to 1/2 at squared. Well, that doesn't leave us much option. It tells us that the distance is indeed 1/2 at squared. And so this ends our demonstration, but let me just say that this formula is extremely important and very helpful. Oh, not that one, but I guess this one here I'm talking about, that the distance covered by a body subject to uniform acceleration in a straight line beginning at rest is equal to 1/2 at squared, where a is the acceleration. This is a very important formula that we'll have cause to use in the future to ferret out other information about the way that bodies move. So I hope you will stay tuned and watch our other videos about that. Thank you.